Okay, so 7.3 is on polar coordinates. Some of you may have seen polar coordinates before, maybe if you've taken a pre-calculus class. Uh, I know I saw it when I was in high school. Um, didn't know what it was used for until I got into calculus. Okay, so let's go over polar coordinates here. And then we'll get into the calculus of polar coordinates. Okay, so if I want to go from polar to rectangular, I want to change something from polar, okay, coordinates to rectangular coordinates. And okay, then I use the unit circle to help me do this, but not the unit circle. I just use what's called concentric circles with differing radii. Okay, and I say, well, x is equal to r cosine theta. Okay, and y is equal to r sine theta. So these act very much like parametric equations. Okay, x equals r cosine theta, y equals r sine theta. Very similar to parametric equations. And this is if I want to go from polar to rectangular. That will give me an xy. More importantly, how do I convert from rectangular to polar? Okay, to polar. How do I take a r theta or an xy and convert it to an r theta? Okay, so this again, polar to rectangular. Polar is an r theta, and we convert that to an xy. Okay, a radius and an angle give me a polar point. A point on a polar graph is r theta. Okay, rectangular to polar. This guy is if I have, how do I find the angle of a point? Well, let's look at a graph real quick. Okay, this point out in space can be described in two different ways. Okay, this point can be part of a rectangle, or this point could be part of a circle. Okay, so if it's part of a rectangle, we think of this in terms of an and y, x and y value. Okay, if it's part of a rectangle, it has an x and y value. However, we could also think of it in terms of r being the distance from the origin out to the point, that's r, and the angle that this makes with the x-axis, that's theta. And so every point out in space can be thought of in terms of an xy or an r theta. Okay. So if we use rectangular coordinates, we can have it be an xy. If we use polar coordinates, we're going to have this be in terms of, instead of xy, instead of an r and a theta. Okay, I can get to any of these points out in space by knowing what the radius is and knowing what the angle is. I can get to any point in space. Just vary the radius and the angle, and I can get to any point in space. So to go from rectangular xy to r theta polar, okay, I want to figure out some properties of this right triangle because this is an x and this is a y. So how can I find the angle given x and y? How can I find that angle theta given x and y from trigonometry?
but that's only for one inning.
What is it?
The tan theta?
Yeah, tangent, right? Tangent will relate y and x. And if I take the inverse tangent of y over x, then I would get the angle, okay? Keeping in mind that it may not always produce the angle that we're looking for, we have to then kind of test, because the domain of inverse tangent is pi over 2 to negative pi over 2. So it will only produce an angle that is between negative 90 and 90 degrees. But then we would have to say, well, we would have to look at our y and x and know which quadrant it is. And so it will produce, this will produce an angle, but it'll only produce an angle in the first or fourth quadrant. If I'm located in the second or third quadrant, I'll have to do some addition of 180 or subtraction from 180. Okay. Okay, what about R? How would I find R? Given that that's a right triangle.
Pythagorean theorem.
Yeah, Pythagorean theorem, x squared plus y squared equals r squared. And that's how we translate any point in terms of x, y into r theta, or any point in r theta into x and y. Okay. Okay, we using just r related to theta, okay, we'll say r a function of theta gives us polar equations for a curve. Okay, r of theta gives us a polar equation of a curve. Okay, so let's sketch the polar curve where r equals 2 cosine theta. Okay, and find the Cartesian, also rectangular, aka rectangular. Okay, the Cartesian form, the rectangular form, in terms of x and y, equation of the curve. Let's do those two things, okay? Okay, so I'm going to say, here's theta for various thetas. I'm going to do a cosine of theta, and then I'm kind of building my function, okay? This is r, a function of theta, but theta is being acted on by cosine and then on by 2. And then I can say, well, this is going to be an r comma theta. Okay, and we'll see where that r theta is located, okay, on our polar equation. Okay, so let's see what happens when we do, we start with 0. Okay, at 0 we get 1. Cosine of theta is 1, and then 2 times 1 is 2. So we're at 0, 2. Okay, so right away we're at 0, 2. Or sorry, 2, 0, my bad. 2, 0. Okay. What about pi over 4? The cosine of theta is radical 2 over 2. If I multiply by 2, I get radical 2. And so this becomes radical 2, because again, this is r, right? R is equal to 2 cosine theta. Okay, but this is r. Okay, so this is radical 2, and then pi over 4 is the angle that I meant. If I take pi over 2, okay, then I get the cosine to be 0. 2 times 0 is 0, and so I get 0 and then pi over 2. If I take 3 pi over 4, I get negative radical 2 over 2, which is negative radical 2 when I multiply by 2. I cancel out that 2 on the bottom, and I get negative radical 2 and then 3 pi over 4. And then I get pi. Okay, so pi, this will be cosine of theta is 1. Or sorry, it's cosine of theta pi is, no, that's negative 1. All right, that's negative 1. Okay, and the 2, that's negative 2. Okay, and so I get negative 2 pi. Okay, interesting. Okay, and then we could keep going if we wanted to. Okay, but we don't really need to, because we have enough that we need to draw the curve. Okay, normally we would think like, oh, we have to go to 2 pi. But we're going to see that the period for this function is really pi, not 2 pi. So as we start to generate these points, okay, we have to think in terms of angle and radius. So when the angle is 0, when theta is 0, I have a radius of 2. So maybe think of it kind of like a vector. Okay, that I have a magnitude of 2 at an angle of 0. Okay, so I have this point here at 2, 0. Okay, at pi over 4, okay, which is a 45-degree angle, at pi over 4, I have a radius of radical 2. Huh. Okay. So at pi over 4, I have a radius of radical 2. Okay, okay. So how would I get a radius of radical 2? Well, let me see. Maybe I want to make this more to scale, but yeah, let's make this a little bit bigger. I want this to be 1. Okay, and then I'm going to go 1, and then I'm going to go out a little bit further and make it 2. Okay, just kind of over accentuate these items. I'm going to put this radius here. Okay, boom, that's my first one. Okay, so the point is here. Okay, now radical 2 at pi over 4. If we think of a square, okay, if we think of a square, okay, the diagonal of this square, if it's a 1 by 1 square, that's 1, 1. The diagonal of the square is actually root 2. And if it is a square, this angle down here is 45 degrees. So my next point, that's really thick. Okay, my next point is going to be right here at pi over 4. I don't know why it keeps disappearing. Okay, at pi over 4. At pi over 2, where am I at? At pi over 2, which is at a 90-degree angle. At a 90-degree angle, what's the value of r? Well, the value of r is 0. So my next point is here. Okay. Okay. So what I'm getting is I'm getting a curve that goes through these points. Okay, so this is at 2, 0. This is at radical 2 pi over 4. This guy over here is at pi over 2 and 0, right? No, at 0 pi over 2. 0 pi over 2. Okay. Okay, now we get into negative territory. I'm going to actually have to erase that and go from the bottom here. 0 pi over 2. Okay, is that guy. Okay, now we're going to say, well, what happens at 3 pi over 4? Well, where is 3 pi over 4 located? 3 pi over 4 is over here, where this angle is now 45 degrees. Okay, maybe I'll extend this out a little bit more. Okay, and so, but it tells me that the radius is not positive, it's negative. So what does it mean for the radius to be negative? It means that if it was positive, I would get a vector to look like that. I would get the point at the head of this vector to look like that. However, because it's negative, I'm going to have to go in the opposite direction. So it actually goes here. And that would be my next point. Okay, so it's going to go there. I'm going to make that black. Okay. I don't know why it not liking the annotation. Let me see. I don't know. I'll have to look at it a little bit later. Okay, so that's this point right here. Like, if I ink it, it will erase. I need to change that setting. That's fine. Okay, and then where do I go for my next point, my last point here? Well, it's at -2 and pi. Well, where's pi? Pi is out here. Okay, if I were to go 2 in the direction of pi, it would be this direction. However, it's -2 in the direction of pi, which means that I'm actually going the opposite direction, which means I'm going this way. And I just end up back where I started. Okay, and so we're going to continue the curve. Okay, and we get a circle. Okay, we get a circle. We get a circle of radius 1. Okay, a circle of radius 1. Okay, and it's oriented along the diameter is along the x-axis. Okay, so we actually get a circle of radius 1 centered at 1, 0. Okay, it's centered right here at 1, 0. Okay. Okay, so let's show that that is true even in rectangular coordinates. The polar equation that they gave us was r is equal to cosine, or r is equal to 2 cosine theta. But how do we change this to x and y? Well, we know that r that x is equal to r cosine theta. Okay. So if we divide both sides by r, we get cosine theta is equal to x over r. That's just the ratio of the x to the radius. Okay, the x value to the radius, that's our normal cosine ratio. And what I'm going to do is I'm going to replace that. I'm going to plug that back in here. I'm going to get r is equal to 2 times x over r. Now I'm going to multiply both sides by r. I'm going to say r times r is equal to 2x over r times r. I'm going to cancel out that r. I get r squared is equal to 2x. Okay, but what do we know r squared to be? Well, from the Pythagorean theorem, we know r squared is x squared plus y squared. If I toss the 2x to the other side, I get x squared minus 2x plus y squared equals 0. If I complete the square, I take half of negative 2 and square that. I'm going to add both sides by that number, and that number just happens to be 1. So this is x squared minus 2x plus 1 plus y squared is equal to 1. If I factor this, which is why I completed the square, I'm going to get x minus 1 squared plus y squared equals 1. And that is a circle in rectangular coordinates. This is a circle centered at 1, 0 with radius 1. So even in polar coordinates, we get a circle, okay, and in rectangular coordinates. However, one thing that we need to notice here is that to get the circle, to get one cycle of this circle, I only go from 0 to pi. Okay, that will give me one cycle. If I had to go 2 cycles, okay, if I went from 0 to 2 pi, it would give me 2 cycles. And it's very similar to what we did with one of the cases for the parametric equation. We had x and y. Polar is kind of it's a specific type of parametric equation. However, when we take it in r is equal to r of theta, we put the function in terms of r of theta, we kind of eliminate the parent parameters x and y. Okay, then we're just dealing with a true polar function. But again, 0 to pi gives us a circle. If we were to go to 2 pi, we would actually end up going around this circle twice. Okay. So we could say that the period is equal to pi. Okay, let's try another one of these. Okay. Let's sketch r equals 1 plus, oops. Okay, r equals 1 plus the sine of theta. Okay. Let's sketch this. Okay. Now, it may not be completely evident, like you have to have a lot of points to make this thing kind of look like what it is, and it may not even be completely evident when you sketch it exactly what it looks like. The good thing is that you can do polar equations in Desmos. And so Desmos will give you an idea of what you're looking at. Okay, but I don't want to, give away the punchline here too early. We'll put this in Desmos, and then when we're done trying it freehand, okay? But you'll begin to see like, oh yeah, that's really kind of what it's supposed to look like. Okay, but I do want to get enough data points, enough points to kind of get a good idea of what we're looking at here. So we're going to do a theta, sine theta 1 plus sine theta. And then we're going to say, well, what's our r theta? Okay, because the 1 plus sine theta, that's my r. Right? Okay, so I'm going to actually have 1, 2, 3, 4, 5, 6, 7, 8, 9 data points here. So we're going to have 9 points that we're going to get. Okay, so let's start at 0. The sign of 0 is 0. 1 plus 0 is 1. So this is going to be 1, 0. Okay, good. Okay, pi over 4. That's radical 2 over 2. This is 1 plus radical 2 over 2. Okay, which is approximately 1.707. So I'll go 1.707 and then pi over 4. So if you didn't know radical 2 over 2 is about 0.707, well, now you do. Okay, pi over 2. Okay, the sign of pi over 2 is 1. 1 plus 1 is 2, so this is 2 and then pi over 2. Okay, 3 pi over 4. The sign of 3 pi over 4 is still radical 2 over 2. That's 1 plus radical 2 over 2, which is going to be 1.707, and then 3 pi over 4. Okay. Pi, let's go to pi. Pi is going to be, the sign of pi is 0 again. 1 plus 0 is 1. This is going to become 1 pi. Okay, 1 and pi. Okay, 5 pi over 4. Sine of 5 pi over 4 is negative radical 2 over 2. So this is going to be 1 minus radical 2 over 2, which is about 0.293. Okay, so this is 0.293 and 5 pi over 4. Okay, 3 pi over 2. Okay, that's going to be a negative 1. 1 plus negative 1 is 0. So this is going to be 0 and then 3 pi over 2. 7 pi over 4 is also negative radical 2 over 2, which is 1 minus radical 2 over 2, which is 0.293 and 7 pi over 4. And the last one we'll do is 2 pi. That's 0. That's 1, which kind of brings us full circle. 1 and 2 pi, which brings us back to kind of our original point. So in this case, our cycle, our period is 2 pi, because we end up back at the same point, because 0 and 2 pi are the same angle. If we end up at the same angle at the same point, then that's our period. And not all polar equations will have a period. They may not cycle at all. One is r is equal to theta. If you had just r equals theta, that would give you a spiral, and that would not cycle. Okay, but this one actually cycles. It will repeat the loops. And so let's see what we got when we go to graph this thing. Okay, so I'm going to put in our angles that we're going to be looking at. Okay, we've got pi over 2s and pi over 4s. So let's see what we can do here. I'm going to make this a little nicer, actually, because I'm going to be using this graph for the next 2 equations as well. So I want to kind of make it a nice graph. So let's do that. So I won't actually use the ruler here. Okay, get out my ruler. Okay, and oops. I'll make the graph be black. Okay, so I'm going to start with this guy. And then we're going to go to 90 degrees. Then we'll go this guy as well. Okay. I'm going to call this, move this out of the way. I'm going to call this 1. I'm going to call this 2. Okay. So that's 1, that's 2. So how long is 1? 1 is about an inch. Well, it's about 3/4 of an inch. Okay. So if I go here, go 3/4 of an inch. That will give me division here. Okay, and then division here. Division here. Division. Okay. Okay. I just wanted to make sure that I'm pretty accurate with my divisions here. Okay, and then I'm gonna put in 45 degrees and put in some dotted line going down, and then I'm gonna do the same thing for the other 45 degrees. Okay, so that gives us something to work with. That's a little nicer than just freehanding it. Okay, so let's get rid of the ruler. Go back. Okay, so now we're going to say that at, I'm going to zoom this in, zoom in on this. Okay, at 1, we're at sorry, the angle 0, we're at 1. So 1, 0 is right there. Come on, give me my point. Okay, 1, 0 is there. Okay, 1.707, that's a little shy of 2. Okay, and so, and we're at the 45 degree mark. So 1.707, well, radical 2 is about 1.4. Radical 3 is about 1.7. And so, so at 45 degrees, I'm going to go out. Radical 2 would be 1.4, which would actually be this point right here. That would be radical 2, which is 1.41. But we're going to go a little bit further to 1.7. Okay. Okay, so we're going to go out here to about 1.7. If this is 2, that should be, but it's 1.7 along the diagonal. Keep that in mind. It's this guy here. Okay, 1.7 there. Okay. So this guy was at 1. This guy's at 1.7. The next guy is going to be at pi over 2, which is 90 degrees, and he's going to be at 2. Okay, so right there. So he's going to be at 2. Perfect. Okay. And then the next one is going to be at 1.707 and 3 pi over 4. So it's got to be along the 3 pi over 4 line here, that angle. But then we're going to be at, okay, we're going to be a little bit farther than radical 2, which would be the diagonal of a 1 by 1 box. And so we're going to be here. Okay, that's where that guy goes. Okay, and then maybe I'll put these dots in black, just so we know that those are the endpoints. Those are the heads of those. Okay. So now we're gonna go, and where are we at? We're at 1 and pi. So 1 and pi. Okay, so this guy goes here. Okay. And we'll put the dots. The arrows don't exist. It's just the black that exists. Okay, just keep that in mind. The arrows are there to kind of as a reference. Okay, or this is this angle here is this angle is at 0. This angle is at pi over 4. This angle is at pi over 2. This angle is at 3 pi over 4. This angle is at pi. Okay, now let's look at 5 pi over 4. Okay, at 5 pi over 4, where were we at? Well, we're at 0.293. So that's 1/3. Okay, so if we think about in terms of one unit, if we swung this down, okay, we swung this down to 1 unit, okay, if we kind of like swung it down, that would be 1. So we would really want 1/3 of that. So 1/3 of that might be here. Okay, pretty small, pretty small. So 1/3 of that distance. Okay. Little dots that I made. Okay. So it's 1/3 of that distance. Okay. And so the point would go there. And then that's at 5 pi over 4. At 3 pi over 2, I'm actually at 0. I'm back here. At 3 pi over 2, the angle is down, but I'm actually have 0 length. Okay. And then again, I'm at 0.293. Whoops. 0.293. And so we're there. And then we go all the way back to our original starting position, which is 2 pi and 1. So what exactly does this thing look like? Well, it looks kind of like this. If I were to connect these dots with curved lines, it would go like this. Make that a little bit better. And then I keep doing this all at once. Maybe I'll connect them with individual curves. But if I mess up, I have to erase the whole thing. And then it goes through here and goes in, and it goes through there and goes back around. This thing is called, okay, a cardioid. Okay, because of the heart shape that it has. Okay, it's a cardioid. Mhm. Now, my graph is not going to be as nice as, okay, this would be 2.5 and this would be 3, right? Go up more. We'll just put 3 there. Okay, so this is 1, this is 2, this is 3. Now, cardioid, right? Cardioid, yeah. Okay, heart shape. Okay. So, the cardioid or the heart shape, okay. Okay, kind of looks like that. Now, we can go to Desmos and look at what this thing looks like being computer generated. So if I type in, okay, R, okay, so can I get my R, oops, I didn't want capital R, I want lowercase r. R is equal to, okay, 1 plus the sine of theta. Okay, so actually let's go back to this. Functions, do we have the sine? Yes, the sine of, let's go AB, see the sine of theta, and we're going to do a close parentheses here. I can find my parentheses. There we go. Okay. So now we have our cardioid. Okay, and you can see like theirs is a lot nicer than mine because theirs is done on a computer with thousands of points, and I only graphed mine with 9 points, which is not too bad for 9 points. But no, okay, we're gonna keep that cardioid. We're gonna put it to the side for a second. Okay, because we want to do some calculus on this. Okay, so let's first discuss like how do we do calculus on this shape? Okay, and we're just gonna look at right now. We're gonna look at uh, derivatives or tangent lines to, what's the slope of the tangent line to a polar curve. Next, this Thursday when we come back, we'll talk about arc lengths and areas for polar curves, and then generalize that for parametric equations. But let's figure out how do we find a derivative of a polar curve, and what does that mean? Okay. Okay. I mean, my cardioid's not horrible. Okay. Try to do as best a job as I could. Yeah, hopefully you get the idea. Okay, so we're gonna put our cardioid to the side for right now, and then we're gonna say what are derivatives in polar coordinates. Oops. So derivatives in polar coordinates. So dy dx But we don't have something in terms of dy dx. We have is something in terms of r and theta, right? R of theta. So we're thinking like, how do we find the derivative of dy dx in terms of r and theta? Well, we have to change parameters. Okay. Okay, so dy dx we can say is the same as dy d theta over dx d theta. Kind of very similar to what we did with the parametric equations, right? Dy dt over dx dt. But now we know what these are. We could actually plug these in. See, because y is equal to r sine theta, and x is equal to r cosine theta. Okay, so if I take the derivative of y equals r sine theta, now r is a function of theta. Keep that in mind. R is its own function. So it's not a constant here. Okay? So if we take y prime or dy d theta, okay, this is going to be a product rule, which is going to be the derivative of r, which is dr d theta times sine theta, plus r times the derivative of sine, which is just cosine theta. Okay, so that's the derivative of y with respect to theta. Okay, x, let me move this over a little bit to the right. Okay, dx d theta is equal to dr d theta times cosine theta, that's the derivative of the first times the second, plus the derivative of the, or sorry, plus the first times the derivative of the second. Well, this is r times negative sine theta. So if I wanted to simplify that, I could just pull the negative outside. This positive becomes a negative, and then I could get rid of the negative and the parentheses here. Let me get rid of the negative in the parentheses. That just becomes r sine theta. Okay, so this thing up top actually becomes, okay, dr d theta times sine theta plus r cosine theta all over dr d theta times cosine theta minus r sine theta. And that's how we find the derivative, okay, dy dx in polar coordinates. Right? Okay, let's do an example with this. Okay, for the cardioid, we found in example 2, r equals 1 plus sine theta. Okay, find the derivative when theta is equal to pi over 3. Okay, so when theta is equal to pi over 3, let's find the derivative of this thing. Okay, so we need to know what is dr d theta. Okay, because again, dy dx is going to be equal to dr d theta times sine of theta plus r cosine theta all over dr d theta times cosine theta minus r sine theta. So we need a couple of things. We need to know what's r equal to. It's 1 plus sine theta. And then what's dr d theta? Well, that's the derivative of r with respect to theta, which is just going to be cosine theta. Okay, the sine turns into a cosine when I take the derivative. Okay? So now what I can do is I can replace, every time I see an r, I'm going to replace it with 1 plus sine theta. And every time I see a dr d theta, I'm going to replace it with cosine theta. Okay. Okay, so dy dx is equal to cosine theta sine theta plus r, which is 1 plus sine theta cosine theta, all over okay, cosine theta minus 1 plus sine theta sine theta. Okay. Okay, so let's try to simplify this. Let's distribute. We get cosine theta sine theta plus distribute this. This is cosine theta plus sine theta cosine theta. Okay, so I've got two of the same thing here on top. Okay. And then we've got a cosine squared theta okay, minus, I'm going to distribute the negative and the sine at the same time. Okay, minus sine theta minus sine squared theta. Okay. So this is going to be equal to 2 cosine theta sine theta plus cosine theta, got two of those, over cosine squared theta minus sine squared theta minus sine theta. Now from trigonometry, you might recognize these. These two are double angles. Okay, the top one is sine 2 theta, and the bottom one is cosine 2 theta. Okay, and so that's dy dx. That's my derivative. Now we wanted this at, okay, at theta. We want to evaluate this at theta equals pi over 3. Okay. Let's plug in pi over 3 into this expression that we got here. Okay, so the derivative dy dx is equal to sine of 2 pi over 3 plus the cosine of pi over 3 all over the cosine of 2 pi over 3 minus the sine of pi over 3. Okay, so the sine of 2 pi over 3 is radical 3 over 2. The cosine of pi over 3 is 1/2. The cosine of 2 pi over 3 is negative 1/2. And the sine of pi over 3 is radical 3 over 2. If I factor out a negative on the bottom here, I get radical 3 over 2 plus 1/2 all over negative 1 times 1/2 plus radical 3 over 2. Well, notice that the top and the bottom are the same thing. Those cancel, and I'm just left with negative 1. So my dy dx is equal to negative 1. Okay, and this is the slope of the tangent line. 2 r equals 1 plus sine theta at pi over 3. It's negative 1. It's a negative 1 slope. Okay. For number 4, what we're going to do is we're going to find the equation of the tangent line using the slope. Find the equation of the tangent line to r equals 1 plus sine theta at pi over 3, at theta equals pi over 3. Okay, we know that dy dx is equal to -1. That's from number 3. Okay, from example 3, I should say. Okay, so the dy dx, I just need to know what to get the equation of the tangent line. I need a point and a slope. So I need a point at pi over 3. So I need to know, okay, at pi over 3, where is this point located? If we go all the way back to our cardioid, if we take an angle of pi over 3, okay, we take an angle of pi over 3, I want to know where is that point located? Okay, and I want it to be located in the in the xy plane. Okay, where is that point going to be located? Okay, in the xy rectangular. I want a rectangular point because I need a y, an x, and a y. Okay, so where is that point going to be located when theta is pi over 3? Okay, so let's see what we can get here. Okay, so we know that x is equal to r cosine theta and y is equal to r sine theta. Okay. Okay, well, what is r? R is 1 plus sine theta. So x is equal to 1 plus sine theta times cosine theta. And, okay, y is equal to 1 plus sine theta sine theta. Okay. So this is going to be x equals cosine theta plus cosine theta sine theta. That's the x value. If you just give me the theta, I can give you the x value. And y is going to be equal to sine theta plus sine squared theta. Okay, so again, where is theta? Theta is equal to pi over 3. So let's plug this in. So x is going to be the cosine of pi over 3 plus the cosine of pi over 3 times the sine of pi over 3. Okay, well, the cosine of pi over 3, okay, is 1/2. Okay, so that's 1/2 plus the cosine of pi over 3, again, that's 1/2, times the sine of pi over 3, which is radical 3 over 2. So this becomes 1/2 plus radical 3 over 4. If I get a common denominator, this will be 2 plus radical 3 over 4. And that's where x is located. X equals 2 plus radical 3 over 4. Okay, where is y located? Well, y is equal to the sine of pi over 3 plus the sine of pi over 3 squared. Okay. So the sine of pi over 3, okay, is radical 3 over 2. So this is radical 3 over 2 plus radical 3 over 2 squared. Okay, so that's going to be equal to radical 3 over 2 plus radical 3 times radical 3, that's just 3, over 4. Okay, so if we multiply both top and bottom here by 2, I will get 3 plus 2 radical 3 all over 4. Okay, and that would be my y value. So y equals that. So now I have an x and a y. I have 2 plus radical 3 over 4, comma 3 plus 2 radical 3 over 4. That's my x and y. And I have a slope. Okay, I have a slope at this point of tangency of -1. So now I can just use the point slope form. I get y minus y1 is equal to m times x minus x1. Okay, y minus 3 plus 2 radical 3 over 4 is equal to negative 1 times x minus 2 plus radical 3 over 4. Okay. Okay, so y minus 3 plus radical, oh, sorry, 3 plus 2 radical 3 over 4 equals negative x plus 2 plus radical 3 over 4. Okay. I'm going to add 3 plus 2 radical 3 over 4s to both sides. 2 radical 3 over 4s. Okay. So this becomes y equals negative x plus, now I can just add the numerators here. And that's going to be plus 5 plus 3 radical 3's over 4. Okay. And so that's the equation of my tangent line. Okay, so, well, how does this help me? Well, I can graph this equation of the tangent line at the point of tangency, where theta is equal to, this is where theta equals pi over 3, right? It would help me if I got a decimal equivalent if I'm doing this freehand. Okay, what is the decimal equivalent of 5 plus 3 radical 3 over 4? Well, let's see what that is. So 5 plus radical 3 over 4. Would be what? This is going to be y equals negative x plus approximately, I'll say y is approximately negative x plus some decimal equivalent, if my calculator ever loads. Okay, so hopefully you can see my calculator. Okay. So we want 5 plus 3 radical 3 over 4. And that's about 2.55. So about 2.55. Okay. So again, that's about 2.55. Okay, why? That's going to be a little more helpful when I go to draw this thing. Okay, so I just need negative x plus 2.55. What's the y-intercept? The y-intercept is 2.55. What's the x-intercept? Yeah, it's also 2.55. Okay, the y-intercept is 2.55, but the x-intercept is also 2.55. If I plug in 0 for y and I solve for x, I get positive 2.55. So I know that 0, 2.55 is a point on the line, and 2.55, 0 is also a point on the line. Okay, so let's go back up to my graph here, my freehand graph, and that was what we're looking at is this point of tangency here. This is pi over 3 and, whatever 1 plus, the radius here is going to be 1 plus radical 3 over 2, whatever that comes out to be approximately for the radius. It doesn't really matter. Okay, but what do I know? I know that 2.55 is a point on the line that I'm looking at, and 2.55 is also a point on this line. Okay, and so my tangent line, okay, Okay, we'll go through, okay, that point here. Again, mine's not going to be as exact as as as- trying to draw it straight. Don't want a straight line because my graph is not perfect. Okay, so we're just going to go like so. Okay, so again, y-intercept, x-intercept, there's my graph. If we were to look at this on Desmos, then bring Desmos back up. Let's graph this equation. Okay, y equals negative x. Okay, plus. Okay, we'll put in the actual value here of 5 plus radical, or sorry, 3 radical 3. Okay, divided by 4. And we can see that we get a point of tangency here. Okay. It's saying if we did, how can I get the point of intersection? If we did, if I did y equals radical 3 x, because remember then I might be able to get the point of tangency. Because if I get a value that goes through 0, 0, and I get, let me write this down real quick. Okay. I mean, I know what I want to do, and I know it's going to be correct, but I just want to go through and tell you what is going through my brain at the moment. So I want to draw the line theta equals pi over 3. Okay, I'd like to draw that line. The problem is that Desmos doesn't understand theta equals pi over 3. Does, however, understand a line. Okay, and theta equals pi over 3 is going to be this angle pi over 3. The problem is I need a point. I need a point on that line. Okay, I need another point in order to draw the equation of the line. And using, we could use the fact that this is a 30, 60, 90 triangle, and that this would be 1, this would be 2, and this would be radical 3. Okay, so when I get this point up here, okay, this point is going to be at 1 comma radical 3. Okay, and the point down here is at 0, 0. And so when I look at the slope of this line, slope of that line is going to be y2 minus y1 over x2 minus x1, which is going to be radical 3 minus 0 over 1 minus 0, which is radical 3. So the slope of that line is radical 3. So the slope of the line that has pi over 3, that theta equals pi over 3 line, the slope is radical 3 and it goes through 0. So I know that the equation of this line here is y equals radical 3x. So when I go back to Desmos, okay, when I go back to Desmos and I plug in the line y equals radical 3 x. That should be the line. Okay. And that should give me the angle pi over 3. And that gives me a point of intersection on this curve. Okay. Between these 2 points. Okay. It gives it to me in not in polar equation form. It gives it to me in rectangular form, the point of equation, the point of intersection. But again, we do see that this line goes through 0, 2.55 approximately, and 2.550. And so yes, that is the tangent line at the angle pi over 3 for this cardioid. Okay. Okay, and that is section 7.3. Okay.